In this video, I will very quickly go through a D flip-flop, more specifically an edge-triggered or positive edge-triggered D flip-flop. Right? So again, we don't really concern ourselves as to how the design is built, so we just work with the black box because the tool will end up building the design for us anyways. The only thing that you need to know is that every time you see this triangle near the clock, that means that this is a positive edge-triggered D flip-flop. And if you see a bubble at the input, then that makes it a negative edge trigger. And then a D flip-flop basically has a D line. D also stands for data, and a Q. Q output is general. It's standard. It's convention. So some textbooks also have Q and Q bar, two outputs. We will just work with one because we just need one. And then we also have a reset input for our design. So the way this D flip-flop works is when my reset is 1, let's assume that it's an active high reset. So when my reset is 1, and there's a rising edge on the clock. Rising edge meaning that the clock goes from 0 to 1. So you see this up arrow? That's basically a rising edge. Or it's also called a positive trigger, positive edge trigger. So right, when my reset is 1 and there's a rising edge on my clock, my Q goes to 0 irrespective of what my data is. Okay? And then let's say my reset goes back to 0. Now on every rising edge of clock, whatever my data is, if D can be 0 or 1, that gets transferred into my Q output. And if my clock is 0, then whatever my data is does not matter. Q remembers its previous value. So if you were to write a truth table, it's also called a state table of what a positive edge trigger D flip-flop might look like. It's something like this. So let's say that data is 0 and there's a rising edge of clock. Then my Q goes to 0. If my data is 1, clock is 1, or clock is on a rising edge, then Q becomes 1. I know if my clock is 0 and does not matter what the value of my data is, you see Q equals to Q minus. So Q minus is a convention. What Q minus basically means is it's the previous state. Okay? So in the previous case, my Q was 1. So in this case, irrespective of what my data was, because the clock is 0, Q remains a 1. Now, this is a little tricky to understand, but let's say my D is X and clock is 1. Q, it's safe to say Q is still the previous value. The reason being, so let's assume that this is my clock signal, right? So you see it goes from 0, there's a rising edge, and then it falls down, right? You see there are two cases, case A and case B. In both cases, the value of clock is 1. You see clock is 1 and clock is 1. But if this clock is 1, during B, case B, because it's not near to the rising edge, the value of D does not get updated to the value of Q. It remains the old value. But if this clock is 1 near to the rising edge, then whatever the value of data was, D gets updated to Q. So it's a little tricky. So it's just safe to say that only on the rising edge, whatever my data is, goes to Q. And when my clock is 1 or clock is 0, it just remembers the old value. That's an easy way of putting it. Next, let me show you a template or like a Verilog template on how to implement a D flip-flop. Okay, so let me say my D flip-flop is called D flip-flop. Inputs are data, clock, reset, and Q. We know that inputs are data, clock, and reset. Output is Q. And because I'm using behavioral Verilog, it has to be of type reg. It's a Verilog definition. Okay, next. Remember that I'm only monitoring the positive edge of my clock. So always add pos edge clock. So it's not one word, but it's pos edge space clock. So on the positive edge of my clock, begin, end. If my reset is 1, so double equals to means if reset equals to 1, my Q becomes 0. Else, whatever my data is, it goes to my Q. So my Q becomes data, right? So this type of assignment, the less than equal to, it's called non-blocking assignment. And you all probably know the difference between blocking and non-blocking. Just a side rule of thumb is every time you see a pos edge or neg edge, always use non-blocking. So always use non-blocking assignment if you see a pos edge or neg edge. So you keep that as a rule of thumb. A lot of textbooks won't tell that exclusively. Okay, now let's say that you forgot the difference between blocking and non-blocking, or you're a little unfamiliar. Let's explain that real quick. Okay, now, so let's say this is the design that I want to build. I take my edge trigger D flip-flop, I take another flip-flop, I have my data input, the output of one is the input of the another, and then I have my Q2, and all of them share the same clock. So this is the design that I want to build. If you're not familiar with this is actually a shifter design. A shifter is basically an easy way of performing a multiply by 2 or divide by 2. Okay? Next, let's say that you want to code this in Verilog, but you didn't know the difference between blocking and non-blocking. So blocking, by the way, is the equals to sign. Non-blocking is the less than equals to sign. So this is basically the body of my code. The only thing that you should be really looking into is, you see, Q1 is D, Q1 equals to D, and Q2 equals to Q1. So the way blocking assignment works is it first executes this line, and only then does it execute this line. So it's sequential that way, or it happens one after the other. I think that's a better way of putting it. So what the tool will do is it will first set the value of Q1 to D, and then it will go to the next line. It will see that Q2 is set to Q1, but because Q1 is already allotted the value of D, it's going to set the value of Q2 to D as well, right? So if you look at, now if you basically look at your tool and look at how it's implemented this design, it will implement it like this. You have one D flip-flop, your data input, your clock, and your Q1. That's taken care of. But for the next stage, instead of setting my Q2 equals to Q1, because Q1 is evaluated to D, it already does this for me. It implements it this way, which is incorrect, right? I want my circuit to be implemented this way. So the correct way of actually implementing this circuit is like this: Q1 non-blocking D, Q2 non-blocking Q1. And again, this is non-blocking, and you do this, and you will end up getting the circuit like this. Again, so by this, you again want to follow the rule of thumb. You see a positive or negative, and then you use a non-blocking statement. Thank you.